Hi, I'm Jamie McCusker with Rensselaer's Tetherless World Constellation, and we're presenting NanoMine, a knowledge graph for nanocomposite materials science. NanoMine is a collaboration between Rensselaer Polytechnic Institute, Duke University, the University of Vermont, and Northwestern University. So our materials science knowledge graph, NanoMine, is actually composed of three major components. The first is the ontology. The NanoMine ontology is an extension of the semantic science integrated ontology, or SIO, which provides all the properties and the basis for subclasses in the NanoMine ontology. The NanoMine knowledge graph actually provides instances against that ontology and has over 2,000 experimental samples of polymer nanocomposites. And the NanoMine YIS instance itself actually provides the platform for publishing and exploration of that data. So you're probably wondering what a polymer nanocomposite is. You can think of a polymer nanocomposite as essentially a very small raisin pudding. So raisin puddings basically have a bunch of raisins in them, and then there's the pudding base. In polymer nanocomposites, you have fillers and matrices, and a raisin pudding polymer nanocomposite is the raisins are the filler, and the pudding itself, whether it's rice pudding or vanilla pudding, is the matrix. And depending on what you do to the raisins or to the pudding, how you make it, how many you put in, whether you bake it, whether you're putting in currants or cranberries or raisins or whatnot, it will change a lot of features about the pudding, mostly how it tastes. Now imagine your raisins were electric. So if you have a polymer nanocomposite, the filler that you put in can change the electrical properties, the mechanical properties, the thermal properties, and many other aspects of the material, both in terms of how many you put in and what shape they are, and what kind of surface you might put on them. And this all needs to be captured in the knowledge graph. So we've put a lot of time and effort into making sure that we represent all of these pieces. So as I was saying, the Semantic Science Integrated Ontology, or SIO, actually provides the basis for the NanoMine ontology. It provides a number of properties and upper-level classes that allow us to talk about things like attributes of objects, the fact that they're objects versus processes, roles, relations of things in space, time, and how information is organized. One of the main things we're interested in with NanoMine is the properties of these nanocomposites. So we've spent a lot of time modeling many different properties as subclasses of NanoMine property, which is usually a subclass of SIO quantity. And we provide the ability to express the unit of measure, the fact that these might be dependent variables in relation to other measurements, or have uncertainty ranges. And this actually allows us to express a lot of information that had been expressed in many different ways across the XML files. It's also really important to know what kind of raisins you're putting in your pudding. So we provide the ability to say that a polymer nanocomposite has component parts of both a matrix and a filler. We give a type as the actual chemical type. So if you have titanium dioxide, that is the type of the filler. And we give them roles so that we know which is which. And fillers can also have surface treatments. We also need to know how our pudding is made. So some puddings are baked, some puddings are mixed, some puddings are cooled, and the same thing is true for polymer nanocomposites. There are many different processes that can occur, and usually there's multiple steps along the way, and this representation allows us to capture all of that. And then finally, we use nanopublications to capture the provenance of how this knowledge is created, both in terms of measuring particular properties and what devices were used, but also in terms of the paper that we are citing and curating the information from, And finally, the actual processing is available as part of the provenance as well. Here's an example of a fragment of the knowledge graph around a particular polymer nanocomposite sample, and we have the ability to talk about the mass fraction, the composition, the fact that it has a permittivity of a certain level, and essentially kind of ties together all the examples from the previous diagrams. So we use YIS, the open source knowledge graph framework, as the basis for publishing and managing our knowledge graph. Some of the benefits of YIS is the fact that you can build custom user interfaces and reuse existing user interface tools and capabilities that are built into YIS. It also offers the ability to curate knowledge from many diverse sources, and also allows us to infer new knowledge as new pieces come in. Okay, let's show you how the NanoMine interface works. This is the YIS faceted browser configured to work with Polymer Nanocomposites. We can pick a number of properties from a pull down, and also do a autocomplete. We can just start typing in the search box. And we can also pick the filler and matrix types, either filter or fetch all of them. We can also pull back properties on other pieces of the graph. So here we're grabbing the mass fraction, which is important relative to the glass transition temperature. And so the glass transition temperature is actually what happens when rubber gets stiff and glassy. And so it can be very important for the kind of material, for certain kinds of materials. As you can see here, we can pull this down as a table, and we can also visualize all this data as different kinds of charts as well. So right now we're going to pick the mass fraction as the x-axis because it's an independent variable, and the glass transition temperature as the y-axis. You'll note we were able to set mass fraction to log scale, helps see things a bit better. And then we can actually pick a color for the filler material, or we can change it to the matrix material, and essentially get a sense of how these different materials play out and where their property domains are, and how they respond to the density of the filler in the graph. Another thing we can do is we can also change. There are a number of different kinds of charts in here. So, for instance, we can see a heat map that shows the overall glass transition temperature of different types of materials relative to their two different changing the matrix or the filler. And we can also render these as box plots, so we can see how these different properties play out over ranges within certain categories. Here it's as the filler, and we had the matrix before. We also have the ability for power users to be able to create custom charts of their own using the Vega Lite specification language and a Sparkle query. We have a number of charts available in the knowledge graph already that our material scientists have produced so that they can show different aspects of that knowledge graph. And one interesting thing about these charts is that you get a URI for each one. You can publish it and access its metadata. And when you go there, it will be rendered. You can also share the chart. You can customize it and make a version of it for yourself. So here's a chart that talks about our electric raisins, and actually tries to show how the conductivity of these materials change based on the kind of matrix and filler that's being used. And you can actually see kind of the overlaps between these regions and see where these other things combine. Finally, you can actually make your own visualizations if you know Sparkle and Vega. The first thing you do is you enter a Sparkle query into the graph, and pasted in one from before, and you can actually see the table, make sure that the results are what you expect them to see, and then you edit your Vega specification, and basically every column in that table is available as a field. We can actually put together a nice visualization. This is the example from the paper, and we have several others in that paper. We can save those visualizations by just giving it a name and a description. And then we can save the chart. We get redirected back to the gallery, and we can find our chart at the end of the list, and we can see it. There. And once it's saved, it has its own URI, and we can share it by sharing that URI. And since it is a entity in the graph like any other, it is actually resolvable as linked data as well. So if you content negotiate for RDF, you will get it. And this is the JSON-LD version of that, just to show that it's possible. This is true for pretty much any for any entity in the graph, including the Polymer Nanocomposites and the ontology classes and so forth and so on. So what's next for NanoMine? So NanoMine is actually becoming MaterialsMine at materialsmine.org, and we are currently adding support for metamaterials, which basically involves adding the ability to talk about the physical geometries of those materials. But most of the properties are the same, and quite a bit of the modeling is the same. The one other inclusion is we're going to be adding something called Data Voyager, which is the ability to create Vega specifications using a user interface by the actual Vega people. And we're also going to be integrating the faceted browser much more closely with Save Visualizations so that they use some of the same tools. And finally, we're going to expand the use of YIS inference agents. Right now, we're using them for semantic ETL, but we will add the ability to convert units within the graph automatically, simply by knowing that the units are of the same type. Be able to derive computed properties based on mathematical equations that we can express in the ontology. Provide the ability to do quality control within the graph, and a number of other capabilities. NanoMine is available at materialsmine.org, and YIS is available on GitHub at github.io/tetherless-world/YIS. Thank you for watching today, and I hope you can explore more with NanoMine and the future of MaterialsMine, as well as YIS itself. Thanks again.